All right, gang, Math 5500, more on Anova Table for regression. Wow, Anova for regression. We're actually trying, I let the cat out of the bag there. Um, we're actually building up to create what's called an Anova Table. But what I want to do is I just want to demonstrate using R to calculate the sum of squares total, sum of squares regression, sum of squares error. Now, what you can see that I've done is I've loaded uh, body fat. So unlike a face-to-face class where we'd be in a classroom, I'd need to stop. And so if you want to load this and follow along, just pause me. I'm like I'm always here. So anyway, I looked at a model. I'm predicting body fat from triceps, and this is what our model looks like. Now let's switch focus to our sum of squares. The first thing I want to do is create. Well, I'm not going to create the sum of squares total. I'm not going to sum it just yet. But if I want to create the sum of squares total, remember it's just the difference between the observed y and the mean. So what I would want, and of course squared. So what I would want is the y's are body fat. And I want the mean body fat. And I want to square those. All right. Sum of squares regression is going to be my predicted. So here I would have my fitted for the model. So that's my, well, actually, let's do predict. Minus, of course, the mean. And the sum of squares error is just going to be, I could just get the residuals, but I'm gonna just go ahead and create those. So what I could do here is take the observed, which is just body fat, minus the predicted, and square those. All right, so if I sum the sum of squares total, I get 495 point stuff. If I sum the sum of squares regression, I get, all right, something is not working here. What's going on? There's my fitted, should give me the same thing. What happened here? Boys and girls, what's going on? Oh, made a silly one. And then sum of squares error is this. So we can see that sum of squares, or the sum of the sum of squares total, equal the sum of the sum of squares regression plus sum of the sum of squares error. Well, I thought it'd give me a true or false statement, but yeah, anyway, we can see that those, the 352, let me do it, just 352, sorry. And 143.1197 is precisely 495. Sorry about that. That was clumsy. I probably should redo the video, but I'm not going to. Mistakes happen, right? Now, the next thing we want to do, and I'm gonna get out of R now and just go full screen here. The next thing we want to do is move this into the mean square. That seems a little fuzzy, doesn't it? Let's see if we can clean it up just a little bit. Okay, it turns out that we can transition the sum of squares into the mean square. So sum of squares to mean square. And you should know from the previous video, it's just dividing by the degrees of freedom. So the sum of squares total has degrees of freedom equal to n minus 1. The sum of squares regression has degrees of freedom equal to 1. And the sum of squares error has degrees of freedom equal to n minus 2. So we can see that the degrees of freedom for the sum of squares total equals the degrees of freedom for the sum of squares regression plus the degrees of freedom for the sum of squares error. So on the right side, sum of squares regression is 1 plus n minus 2, which of course is n minus 1, which is just exactly the sum of squares for the total. Now, the rest is pretty straightforward stuff. So the mean square for the total is equal to the sum of squares for the total divided by its degrees of freedom. And since the degrees of freedom is just n minus 1, it's just sum of squares total divided by 1. The mean square error term is the sum of squares error divided by its degrees of freedom. So that's going to be the sum of squares error divided by n minus 2. And the mean square regression is just the sum of square regression divided by its degrees of freedom. So that's the sum of squares regression just divided by 1. We just have one predictor, beta, well, other than the intercept. So what we can do easily is we can calculate each of the mean squares just by dividing by its degrees of freedom. Now, the way we typically organize this is in an Anova table. And I'm going to give you an Anova table. And what we have is, in the first column, we have a source. So we're going to have our regression source or our model, our error, and our total. The sum of squares is going to be given in the next column. So here we know that the sum of squares for the regression is the sum of the y sub i's minus the y hat sub i's, the sum of the errors. Wait a minute, I got that wrong. Okay, I can't handle that. Let me grab another piece of. I got that. I got the regression wrong. So again, Anova table. Source, regression, error, and total. So the sum of squares is going to be, for the regression, is the sum of the y hat sub i's minus the y bars. This is the observed minus the predicted. And of course the total is just the difference in the y sub i's and its mean. The degrees of freedom is equal to, for the regression, is just 1. For the error is n minus 2. And for the degrees of freedom is n minus 1. The next thing we look at is the mean square. Well, the mean square is just the sum of squares divided by the degrees of freedom. So in this case, it's just the sum of the y hat minus the y bars squared divided by 1. The mean square for the error is the sum of the observed minus the predicted divided by n minus 2. And the total is the sum of the y sub i's minus the means over n minus 1. Let me put that in parentheses. Now, note that these are additive. These are additive, not additive. In other words, if you take the mean square for the regression plus the mean square for the error, you do not get the mean square for the total. And because of that, when we're constructing an Anova table, we typically eliminate that entry. So for our table, we go back to R. And we could see that the sum of squares regression, when I did it correctly, was 352.3. The error term was, sum of squares for the error was 143.1. And the total was 495.4. The degrees of freedom here would be 1. The error is n minus 2. Looks like we have 20 entries, so n minus 2, 20 minus 2 would be 18. And so we would have 19 here. The mean square would be 352.3. I'll grab my calculator real quickly. The mean square error term would be 143.1 divided by 18. This would be 7.95. And I'm going to illustrate this. The total would be 495.4 divided by 19. This is, I don't know if I did it correctly, is 26 point something. Again, we don't include that because those the mean square regression and the mean square error don't add up. All right. Well, that's it for this video.